Good morning, students. Now I would invite Prachi ma'am to start the session.
Hello everyone, good morning. So how are you all doing? And I hope everyone is awake and ready for the class. So who are all are there in the class? Just mark your attendance. So we have Harika, Bhavna and Omkar, right? So yes, you have to start with typing the answer for the question that I gave you last time, right? So I gave you two questions. So just type the answer of this particular question, which was asking about the wave number. So type the answer for the wave number. We'll start with that and then we'll quickly revise whatever we have learned in the last session, and then we will learn about the electromagnetic spectrum. So yes, who all are there in the class? So type your answer or else just type yes, and then we will begin with the dual nature of electromagnetic radiation. So till now, what we have learned is we were learning about the different models for the atom. So in that we learned about the J.J. Thomson and the Rutherford model. And then we learned that uh, before before Bohr gave his model, he considered the developments that were taking place at that time. So in that, we have to learn about the two developments, and the first one was the dual nature of electromagnetic radiation, and the second one that we have to learn is the experimental results regarding the atomic spectra. So right now we are learning about the dual nature of electromagnetic radiation. When I say dual nature, then it means that we will be learning that light has two nature, that it behaves as a wave and it also behaves as a particle. And what are the electromagnetic radiations and how are they generated? That we have learned in the last session. So what did we learn in the last session about the wave nature of the electromagnetic radiation? We learned that whenever I have a charged particle which is accelerating or which is oscillating, then with that there is a generation of the electric and the magnetic field, right? And if this charged particle is accelerating, then there will be a change in the electric and the magnetic field. And that's how I will get the electromagnetic waves. So how do we define the electromagnetic waves? Electromagnetic waves can be defined as the combination of electric and magnetic field that is traveling in the space. So in that, we learned that these waves, they will be traveling in the space like this. So on one side, I have the electric component and the magnetic component will be at the angle of 90 degree. So this will be your magnetic component, and then you have electric component. So how they are vibrating? One is vibrating like this and the other one is vibrating like this. And both of them are at the 90 degree to each other and also at the angle of 90 degree to the propagation of the wave. So wave, if it is moving like this, then the electric field will be like this and your magnetic field will be like this. So both of them, both of these components, they are at the angle of 90 degree and they are at the angle of 90 degree to the propagation of the wave. So wave is moving like this and these fields are moving like this and moving like this, right? So this is how your electromagnetic wave will look like. So it will have an electric component and it will also have a magnetic component. Then we can pick any of the wave, which is we can pick the electric or the magnetic wave. Why? Because yes, we have to learn few things or few terms related to the wave. So if I have a wave, then the distance between two same consecutive points is defined as the wavelength, the length of the wave, or the other way of saying it is that the distance between the two crust or the 2 trough is the wavelength. That is the other way. So, or else, how do we define the wavelength? The wavelength can be defined as the distance between the two similar consecutive points. And then we learn that what is frequency. So how do we define frequency? So frequency can be defined as the number of waves that pass a certain point in a given second. So the unit of frequency will be hertz, and this is denoted by the symbol nu, and whereas your wavelength will be denoted by the symbol lambda. And then we saw that the reciprocal of the wavelength is the wave number. It is the number of waves per unit length. So simply it's the reciprocal of the wavelength. And the amplitude is the displacement of the wave from zero, or whatever axis we are taking, its displacement from that axis is the amplitude. And also we learned that these waves, they will be traveling at the speed of light, which is 3 into 10 raised to the power 8 meter per second. And the speed of light is denoted by symbol c. And then finally we learned what's the relationship between the speed of light, wavelength, and the frequency. So this is the relationship between the speed of light, wavelength, and frequency, right? So these are the things that we learned in the last class. Now we have to see what are the different kinds of electromagnetic radiations that are around us, right? So whatever light that is coming to us from the sun, there is a very small part of it that we can see with the naked eyes, and rest of it we can't perceive. A human eye can't perceive those radiation. So the light that is coming from the sun, it has many more radiation apart from the visible part which we can see. So let's see what are the different radiations which are the part of the light that is coming from the sun. So in that we have radio waves, microwaves, infrared waves, ultraviolet rays, X-rays, and gamma rays. And this is the wavelength of these waves, which ranges from 10 raised to the power 8 to 10 raised to the power minus 18. Now you can imagine how big this number is. This is in meters. This is in meters. So it is 10 raised to the power 8. So from here what we can say is that radio waves, they have a very large frequency, and that's the reason that these waves are used for the communication, and these are the waves which helps us communicating through our mobile phones, right? And then we have the microwaves, which are usually used in the microwaves for cooking, right? And then we have infrared waves. So any heated object, right? So they will be emitting the infrared radiation. For example, our body. So infrared radiations also we can't perceive with our naked eyes. But yes, we have certain instruments, certain detectors which will detect the heat, right? Also we have, and then we have the visible part of the spectrum. We have the visible part of the spectrum, which is Vibgyor. What we have, which is Vibgyor. So which ranges from red to violet, which ranges from red to violet. And after that, we have the ultraviolet radiations, X-ray, and gamma rays. So which among them will have the maximum energy? So you have to tell me by looking at this spectrum. So this is the whole spectrum actually which we have around us, or the light consists of all of these radiations which are coming from the sun. But there is just a small part, which is this part that we perceive with our eyes, Vibgyor, right? So it consists of the different colors which ranges from red to violet. So W for violet, indigo, blue, green, yellow, orange, and red. So these are the colors that are see, whereas the whole light that is coming from the sun will consist of many more radiation, which may range from radio to gamma rays. Now you have to quickly tell me in the chat which among the following will have the maximum energy. So whether radio waves have the maximum energy or the gamma rays have the maximum energy. So if you know, type your answer. If you don't know, you can simply type no. And it is very important that you interact in the chat so that I know that whatever I am teaching you, you are able to understand it, and then we can move on with the other topics. Yes. So the one which will be having the maximum energy will be the gamma rays. So what you can see here in this plot is, see here the wavelength is more. So the wave, the length of the wave is more, right? So that's the distance between the two same points. Now as I am moving from radio to the gamma rays, which you can see in this spectrum, the wavelength is becoming narrow, or I say the wave is becoming narrow. The wave is becoming narrow. So what I can say is, when I am moving from left to right, or I say from radio waves to gamma waves, right? Also, don't get confused. In your book, it may be the other way around. So you will be given first gamma rays, then X-rays, UV, visible, IR, microwave, and radio wave. So it can be the other way, which is that it can start from gamma and then it can reach up to radio waves. So don't be confused, right? Now, as I am moving from radio to the gamma radiations, then what happens is, here the wavelength. So what is happening to the wavelength? The wavelength is decreasing. What is happening to the wavelength? Wavelength decreases. Wavelength decreases and the frequency increases. The frequency will increase, which we'll see later on why this is happening and how the energy and the frequency, they are related to each other. But for now, you should know that when I am moving from the radio to the gamma radiations, then what is happening is your wavelength, it is decreasing, which you can see here. The radio waves have a very long wavelength, and that is the reason that they will be used for communication, as they can travel the large distances, which is around 10 raised to the power 8 meters. So as I am moving from radio to the gamma radiations, then what happens is the wavelength will decrease, the frequency will increase, and also I can say is that when I am moving from radio to the gamma radiation, your energy is also increasing. So energy increases, frequency increases, and your wavelength decreases. And that is the reason that gamma rays, they are very, very harmful for us. And along with that, ultraviolet radiations is also very harmful for us. So we have the ozone layer, right, which is stopping these ultraviolet radiation. Correct? And yes, we have got the ozone hole. That's why the ultraviolet radiation, they are very harmful for us. So we need that ozone layer to protect us from the ultraviolet radiation. And also you must know that we should not stay for a longer period in X-ray also, right? Because it can cross our body, right? So it will be very harmful for our body. So beyond a point, we should not be exposed to the X-ray. So these are, because they have very high energy. What they have a very, very high energy, right? And as I am moving from radio to the gamma rays, you should know that the wavelength decreases, frequency increases, and energy also increases. So as you can see, the wave is becoming narrow and narrower as I am moving from radio to the gamma rays. So we can say that the frequency will increase, because now if the wave has become narrow, then the number of waves that can cross a particular point will increase. So this we have seen earlier also. So how do we define a frequency? So let's suppose we have this door or we have this point. Now the waves have to cross this point. So I have to see how many waves can cross this point in 1 second, right? So if the wave is shorter, then the number of waves that can cross this point will be more. So if the number of waves that are crossing this point is more, so the frequency will be more. Whereas if the wave is longer, so if you have a longer wave, then the number of waves that will be crossing this point in a second will be less. And what we can see here is, as you can see, as I am moving from radio to the gamma rays, then your frequency is decreasing. You can see here that the rays, they are becoming narrower, right? So here the wavelength is decreasing. So now the number of waves that can pass to a particular point in 1 second will be more as compared to the rays on this side. So this is all we have in the electromagnetic radiation. So we have different kind of radiations, and all of them, whether somebody says you radio waves, microwave, infrared, visible part that we can perceive with our eyes, ultraviolet rays, X-rays or gamma rays, all of them are the electromagnetic radiations. Also, the one important point, the direct memory questions that you can get in the exam is that they can ask you the range of the visible part of the spectrum. So it can ask you in nanometer, angstrom, or meter. So in nanometer, it ranges from 750 nanometer to 400 nanometer. So the range of the visible part, that is VIBGYOR, it ranges from 400 nanometer to 750 nanometer. So it ranges from 400 nanometer to 750 nanometer. Or roughly they can say 400 nanometer to 800 nanometer. And how is nanometer related to meter? Yes, you have to quickly tell me in the chat, how is meter and nanometer related to each other? So 1 nanometer is equals to how many meters? Yes. This we have learned in some basic concepts of chemistry, and also in the last class I explained you for the angstrom, right? That is the unit that we'll be using for the shorter wavelengths. So yes, 1 nanometer is equals to 10 raised to the power minus 9 meter. So Bhavna, you wrote it right, but it has to be the other way around. So yes, you have to put it as 1 nanometer is equals to 10 raised to the power minus 9 meter, whereas 1 angstrom, this is how you write for angstrom. So 1 angstrom is equals to 10 raised to the power minus 10 meter. So the unit conversions, they are very important. So the unit conversions are very important. And what we can see here is that the radio waves, they have a very long, they have a long wave length. They are very long waves, right? That is the reason they are used for communication, which is around 10 raised to the power 8 meter, right? So, and also microwaves, we have around 100 meters, and then the wavelength, it keeps on decreasing as I move from the radio waves to the gamma waves. So yes, you should know that when I am moving from the radio to the gamma radiations in the electromagnetic spectrum, then what is happening to the wavelength, frequency, and the energy. So again, I am repeating this, that when I am moving from the radio to the gamma radiation, then your energy, it increases, your frequency, as you can see here, it is increasing, and your wavelength, it will decrease. What will happen to the wavelength? It will decrease. So the whole electromagnetic radiations, or the radiations that we will be receiving from the sun, most of them, they are stopped there, and then rest of them, it reaches us, right? Also, you may know that in space there is vacuum, right? So the other important property of the electromagnetic radiation is they don't require any medium for their propagation, right? As you may know, for the sound waves, we would require a medium for their propagation, right? Also, if you see the ripples in the water, right? So those are also kind of a wave, but they also require a medium. For example, the waves, they are traveling in water. So if you throw a stone into water, you can see the ripples, right? So they are also a kind of a wave. So all these kind of transmission, they will require a medium, but your electromagnetic radiation, they don't require any medium for their propagation. So if this is clear to you, then we will move ahead with the numerical. So did you solve the problem that I gave you the last time? So if you have solved, we'll see it. If not, you have to solve it, send the answer, and then we will see how do we solve the particular problem. So yes, quickly tell me in the chat whether did you solve this numerical or not. So I gave you that you have to calculate the wave number and frequency of yellow radiation having a wavelength of 5800 angstrom. So quickly tell me whether did you solve this numerical or not. Yes. Yes, Bhavna, Harika, Gayatri, Omkar, Rakshit. So some of them you were not there in the last class, but I hope you have seen the recorded session. So quickly tell me, did you get the same answer for the wave number? So these are just the practice problems. So make sure that you're solving them, because now from here, the numericals, they won't be direct questions, right? You will be getting a simple part like this, and then there will be other things that will be asked related to these same things. So you have to start with the basics, and then practice as much as numericals as possible. So make sure whatever I am giving in the class, solve it so that you can solve more complicated problems. So yes. Hmm. Okay. Yes. Now, we have to calculate the wave number. So for wave number, I need the wavelength, and because the wave number is just the reciprocal of the wavelength. So how do I write the wave number? Wave number is just the reciprocal of the wavelength, right? So do we have the wavelength in the question? Yes, we are given the wavelength, which is 5800 angstrom, and this I have told you that 1 angstrom will be equals to 10 raised to the power minus 10 meter. So now I can convert this wavelength into meters, right? So then I can know what is the wave number. So just I have to take the reciprocal of this wavelength, which is around 1.724 into 10 raised to the power 6 per meter, right? Now, the thing is, why are we even using the wave number when I already have other terms to specify or to tell most of the things about the wave? That is, by the wavelength, I can tell what is the length of the wave. By the frequency, I'll know that what is the number of waves that are crossing a particular area in a second, right? Particular point in a second. So sometimes what happens is, we will have a wave number which will have a very less value, right? So so then we will use the wave number to specify our answer so that we can get a significant number, right? Which you can see here we had the wave number in the power of 10 raised to the power minus 10, whereas now you can see that I have got the wave number as 10 raised to the power 6. Then we can use this larger value, and it makes our calculations easier if I want to use these value at some other places. Now for the frequency, what is the formula for frequency? So as we have learned that the speed of light is the product of the frequency and the wavelength. So from there, we can find out that the frequency will be is equals to C over lambda. And then I put the values for which we know that the speed of light is 3 into 10 raised to the power 8 meter per second, whereas the wavelength is this much. So yes, I can calculate the frequency, which is 5.172 into 10 raised to the power 14 per second. Is this clear to you? So you have to quickly type yes in the chat. So yes, you all have to interact in the chat. Make sure you are interacting in the chat so that I know, yes, you are understanding whatever we are learning, and then we can quickly move on to the next topic. So make sure that you constantly tell me whether you are understanding whatever we are learning, or are you facing any problem. And if you are, you have to ask your doubts in the chat. And then I gave you the other question, which is calculate the wavelength of the ultraviolet waves if frequency is this much, which is 12 into 10 raised to the power 16 cycles per second. So if you see cycles per second, then you should know that yes, they are talking about the frequency. Per second means yes, this is, then unit will be per second. That is it. And you are given the speed of light also. So yes, we can find out what's the wavelength, because C is equals to lambda into frequency. Now, if any of the two terms are given to me, if any of the two variables are given to me, then obviously I can find out the third one. So what is given to me here? I know the speed of light here from this. I know the frequency also. Now, simply you have to do the substitution, and yes, you have to get the calculations right in the exam because you are not provided with the calculator. So make sure that you calculate it yourself. Okay, this is a very important part. Maybe in exam you would be able to know, okay, this is the formula I have to use, this is how you put the values. But the only thing that can get wrong when you are there in the exam is the calculation part. So make sure whenever you are doing questions at home, whenever you are solving any assignments, get the values correct. So, and also be quick with your calculations because you may not have that much time in the exam. So what you have to practice is getting your calculation fast and correct. So make sure that you do as many questions as possible and be quick with your calculation. So these were the two numericals, and these kind of questions you may get in the exam along with some other questions. So yes, from here, there is one formula that you have to take, you have to keep with you, is that we now from here we know what the relationship between speed of light, wavelength and frequency. And also don't be confused with the symbol. This is frequency, this is wavelength, and nu bar is wave number. Nu bar is wave number. Don't confuse nu bar with the frequency. Nu is frequency, nu bar. When I put this thing on the nu, then we say nu bar. How do we read it? We read it as nu bar, which will be known as the wave number. And also you must know, when I'm looking at the wave, what is the wave number, what is the wavelength, what is the frequency, and what is the speed with which it will be traveling in the space. So if this is clear to you, now we have to see, or we have to learn about the particle nature of the electromagnetic radiation. That is what we are trying to understand, right? That your electromagnetic radiations, they have a dual nature. So they behave as wave also, and they are behaving as particle also. So this was the question that at that time, that is around 19th century, most of the scientists, they were also puzzled with the nature of light, right? Whether does it behave as a wave or does it behave as a particle? Now the thing is, initially all of them, they believe that the light, it only travels as the wave or it only behave as the wave. But yes, there were certain experiments, or there were certain observations which can't be explained on the basis of the wave nature of the electromagnetic radiation. And we will be seeing what are those things which can't be explained when we are taking light as a wave. Now, whenever I'm saying light, you should know that I'm saying electromagnetic radiation. So light will consist of all of this uh, radiations which we just saw, right? Because the visible part is just this small fraction of that spectrum, right? So there were many observations, there were many things which they were not able to explain when they were taking light as a wave. Yes, of course, there were certain phenomena which can be explained when we are taking light as a wave. So what are those phenomena which can be explained which can be explained by taking light as a wave? So yes, we can explain the diffraction and the interference. Diffraction and interference of light by taking it as a wave. But yes, of course, there were many things which were not which scientists were not able to explain if they were taking light as a wave. So from there they came up with the answer that yes, light, it behaves as a particle also. So who was the scientist who gave this uh, explanation? Okay, light, it does not behave as wave, it behaves as a particle also. So who was the scientist? Planck, right? Max Planck. So yes, now we have to learn about the particle nature of electromagnetic radiations. So yes, the phenomena like diffraction and the interference, they can be explained when we are taking light as a wave. But yes, there were many things which could not be explained if I was taking light as a wave. Now, first let's see what were those things which were not explained if I was taking, if they were taking light as a wave. So the first one was the black body radiation. So one by one, of course, we learn in detail what is black body radiation. So they were not able to explain the nature of emission of radiation from hot bodies, which is the black body radiations. Also, the scientists, they were not able to explain the photoelectric effect, that is the ejection of electrons from the metal surface. So whenever any light it strikes a metal surface, there will be a ejection of electrons, and that thing was not being able, scientists, they were not able to explain that with the help of the electromagnetic theory, right? And the other things that were not explained is the variation of heat capacity of solids as the function of temperature, and also they were not able to explain the line spectra of atoms, especially for hydrogen. So we learn about the hydrogens, we learn about the spectra of hydrogen. So yes, now you should know that light, it behaves both as a wave and as a particle. So here we will start with learning about the black body radiation. What we will learn about? We will be learning about the black body radiation. So are you ready to learn about the black body radiation? If yes, then type yes in the chat box, and then we will start with the black body radiation, and we'll see what is it that they were not able to explain when they are taking light as a wave. So now from here on, you should know that light, it behaves both as a particle and as a wave, which was a little complex concept for the scientists at that time. For them also, it was hard to accept that light is behaving both as a wave and as a particle. So it was weird for them also to see light as both as wave and as a particle. But yes, there were experiments, there were certain observations which could only be explained by taking light as a particle. So yes, if you want to begin with the black body radiation, then quickly type yes in the chat, and then we will learn about the black body radiation. Yes, what about others? So Gayatri is ready. What about Omkar, Bhavna? So we have Harika, Omkar, Bhavna, Rakshit. So are you people ready to learn about the black body radiation? Yes. Yes, Bhavna and Gayatri is ready. What about Omkar, Rakshit? Are you ready to learn about the black body radiation? Yes, Harika is also ready. Yes, Rakshit, you have to interact in chat. Omkar, you also have to interact in chat, so that I know whatever we are learning, you are able to grasp it. And if not, you have to mention that too in the chat that, okay, ma'am, explain it again. So now here we will start with learning about the black body radiation, right? So first, let's see how do we define a black body, right? And then we will see what is happening and what is it that the scientists, they were not able to explain at that time. So what you should understand here is, by now, like by 19th century, most of the things, most of the phenomena, they were explained using the classical physics. That is the laws that were given by Newton and some other laws, right? But after, once they have observed all these things, then came the quantum mechanics. So from here, it is the beginning of the quantum mechanics. So all of these things which we will be learning right now, they were, so scientists, they were not able to explain all of these phenomena using the classical physics, which were used to explain most of the phenomena, right, on the larger scale. So for the objects which are bigger in size. But when we are observing things at the molecular level, so when I'm looking at an atom, when I'm looking at a molecule, then the Newton laws, or we say the classical physics, does not apply to the, when I'm looking at the microscopic level, which is at the molecules and at the atom. So from here we'll see how we will see the beginning of the quantum mechanics. So you should be excited that you will be learning something new. You will be seeing when did the quantum mechanics start and how it explained the phenomena that were not being explained by the other theories. So let's begin with the black body radiation. So first let's understand what exactly is a black body, right? So a black body is any ideal body which emits and absorbs radiations of all frequency uniformly, and radiation emitted by such body is called the black body radiations. So what it is? So any black body. So for example, let's suppose I have this cell phone, so that body will be black in color, right? So any ideal body which emits and absorbs radiations of all frequency uniformly, and radiations emitted by such a body is called a black body radiation. Now, do we have any perfect black body which will absorb all the radiations and which will emit all the radiations? So practically, in the real situation, we don't have a ideal black body, but the nearest example can be carbon black. So if I'll take a pitch black carbon, then that will act as a black body. That is, whenever light is falling on it, whenever a light is falling on it, it will absorb all the light. So as you may know, for example, right now you can see that this pen is white, right? Now, why is it looking white? Why can't you perceive it as pink or red or of some other color? So it is looking white because what is happening is, if light is falling on it, then what is happening is it is reflecting all of the light, right? So if I combine all the colors that is present in the Vibgyor, if I combine all of the colors, then it will give me a color which is white. So what is happening here is, as the light is striking this pencil, then it is reaching to your eyes, and where what is happening here is that is it is reflecting all of the radiations. It is reflecting all of the colors. It is not absorbing anything. That's why you perceive it as white, whereas something which is absorbing all the light will appear as black. So something which is absorbing all the radiations will appear as black. So what I can say is, black is not a color, right? It is just that whatever light it is falling on that object, it is absorbing all of the light and it is not reflecting anything. So that's why that particular thing will appear as black. Understood? Now, here the scientists, they defined as a black body a object which will absorb all the radiations which is falling on them. And then after a while, once they absorb all the radiation, so if something is absorbing all the radiations, then the temperature will increase. Then after a while, what will happen is, they will emit all the absorption as it is. So what I'm saying is that absorption is also 100%, emission is also 100%, but practically that situation is not possible. We don't have a perfect black body, right? Now what can be the example? Okay, now I'm saying we don't have any perfect black body, but yes, we have the black bodies around you which can emit and absorb the light, right? And the best example is sun. They may not be the perfect black body, but yes, the examples of the black body is the best example sun. The best example is the sun, and also any heated object that you see around you will also act as a black body. So any object which you are heating, then it changes color according to the temperature that I am providing, right? So if I am heating any object, that will also act as a black body, because then once we are heating it, then it will be emitting light of the different frequencies, right? If this is clear to you, then we will see what is it with the black body that the scientists they were not able to explain. But the first thing that you must understand is what is a black body. So black body is anything which will absorb all the radiations that is coming to them. That's why the name is given black, because something which will absorb any everything will appear as black, right? Also, it will emit all the radiations as it is. It will not keep anything with it. So whatever they are absorbing, they will emit as it is. So the perfect black body will absorb 100% of the light, and then it will emit 100% of the light. So if this is clear, then we'll move on to what is it that the scientists they were not able to explain for the black body. Yes. So here we will start with the heating of the objects. So here we will, I'll tell you what happens when we heat a iron rod, right? Also, you might have seen it, right? That when we are heating a iron rod, then what happens is first it becomes dull red, but first it becomes dull red, then it becomes, then the color intensifies, then it becomes more red, and then what happens is as I gradually increase the temperature, it becomes white, and then finally if I increase the temperature more, then it appears blue. It appears blue, right? Now when the scientists they tried to plot the graph for the intensity of light that is emitted to the wavelength. So what they did is they heated an object, and then they observed that what is the color, right? If I am heating it at, let's suppose if they were heating it at 3500 Kelvin, then they observed that the color is something like brown. So as they were increasing the color, the wavelength were shifting. So what you can see here is, so on this side, the wavelength is increasing. So as they were increasing the temperature, there was a shift in the wavelength. So as they were increasing the temperature, the wavelength, so whatever peak we have, this is the lambda max. This is the maximum wavelength that we can get for that particular object at that particular temperature. So if I am heating the object as 5500 Kelvin, then this is the maximum wavelength, this is the maximum intensity, this is the maximum intensity, and this is the maximum wavelength that I can get, right? And depending on the wavelength, we will get a particular color, right? So what they observed is as they were increasing the temperature, then the emissions, they were shifting to a shorter wavelength. What is happening there? The emissions that they were shifting to the shorter wavelength. So we were getting the radiations which were towards the shorter wavelength. And what we have seen in the spectrum is as, so we have VIP, GYOR, right? So as I am moving from here to here, that is from violet to red, your energy decreases, right? And your wavelength increases. So now what I am saying is, as I am moving from here to here, your wavelength, it will decrease. So what I am saying is the energy will increase, right? So the radiations that will be emitted for a hotter object, their energy will be more. And how can I know the energy is more? So they were able to know it by looking at the color, by looking at the color. So this is what they observed is when they started heating the object, initially what happened is there was the increase in intensity. Then the intensity reaches to a maximum for a particular wavelength, and then as with time they start heating it, then what happens is the intensity it decreases. So this is the plot that they were observing, right? This is the experimental data. That is, when they started heating the object, what happened is first the intensity increased, it reached to a maximum point, and then it starts decreasing. And what were they expecting according to classical physics? So their expectation was that when we should start heating the object is that the intensity should increase. So I should get a plot something like this. So where the intensity should reach to the infinity. That was not the observation. We were getting the plot something like this. So now nobody was able to explain this phenomenon, right? Nobody was able to explain why we are getting the plots like this. Because according to the classical physics, or according to what we were expecting light to behave as a wave, according to all those things, it was expected that we should get a graph something like this, which reaches to the infinity. But in reality, we are getting a plot something like this. That is, when I start heating an object, what happens is the intensity of the color, it will increase, it will reach a maximum, and then it decreases. So this is what we will learn. How do we explain this graph? So if this is clear to you, then we will try to understand, we will see who was the scientist and how did he explain these plots for the black body radiation. So any heated object will also behave as a black body, because once you start heating it, there will be a emission of light. And yes, with the temperature, as you can see, the color also changes. So at 4000 Kelvin, so whatever color you see for the lines, that is the color of the emissions. So for this, we'll see that this is at 4000, it will be red. At 4500 Kelvin, it will be orange. Then the color changes from yellow, and then we reach green, and then finally we reach to blue. And then, yes, if it goes beyond these wavelengths, then obviously we'll not be able to perceive it. So below this, they will be emitting IR radiation, and above this, they'll be emitting UV radiations. So if this is clear, then we will try to understand how can we explain this phenomenon. That when we start heating any object, then what happens is the intensity of the light increases, the intensity of the color increases, it reaches to a maximum, and then it decreases. So if this is clear, then we will try to understand why this is happening. So what is happening here is, as the temperature is increasing, lambda may shift to the shorter wavelength, and this is the kind of the plot I am getting, which is as I increase the temperature, what happens is it increases, reaches to the maximum, and it again falls down. So that is how the intensity is changing, right? And as we are increasing the temperature, it is shifting to a shorter wavelength. So this is what was happening. Now we have to understand why this particular thing is happening with the bodies that are emitting energy, right? Because these are the things which we will not be able to explain if we consider light as a wave. Because why is that? Because if I start heating any object, then if I'm treating it as a wave, then it is expected that it should continuously emit the radiation in the form of waves. But here what is happening is it is reaching a maximum, and then again it is decreasing. So this is the plot that I'll get for the particular temperature. That is, first it starts emitting the radiation, the color, and then the intensity decreases. So first the intensity decreases, it reaches to a particular wavelength, and then it starts decreasing. If this is clear to you, then in tomorrow's session, we will learn about the Planck's quantum theory. So from here, the very interesting or the modern physics, the concepts of modern physics, you learn about the concept of modern physics. So this is basically a part of physics, which we are learning in chemistry. So we'll be focusing on the part which is important for us in chemistry. So from here, it began the era of the quantum mechanics, right? So these things, these observations could only be explained by the scientist who was Max Planck, and for this he was also awarded the Nobel Prize. So from here, what he did is, I'll just give you an idea. What he did is that he said that instead of taking light as a wave, he said that it is not in the form of a wave, it is in the form of the particles. It is the form of the particles. We don't see it as a particle because those are moving with a very fast speed. So if any particle, it is moving with a very fast speed, then obviously if we are looking from this point, I'll see it as a wave. If something is moving very fast, then it will look like a wave. But in practical, that was not the case. Your electromagnetic radiation, they behave both as a wave and as a particles. So tomorrow we'll understand how did he explain that your electromagnetic radiation, they behave as the particles, and what is the formula that he gave for giving the energy of these electromagnetic radiation. So the important part for us is the expression for the energy. So if you have doubt in this particular related to this particular session, you can ask in the chat, and then tomorrow we'll try to understand about the Planck's quantum theory. So if you have any doubt, you can ask, and then tomorrow we learn about the Planck's quantum theory, and also make sure that you solve these numericals, and then you will be given many more numericals related to this, which is how your speed, frequency, and wavelength, they are related to each other. So keep these formulas with you, make one sheet, write your formulas at one place, and keep revising them along with the units. You have to be very careful with the units. So if you have any doubt, you can ask. Otherwise, we'll continue this lesson in tomorrow's session. So is this clear to all? If you don't have any doubt, then we will end the session, and then you can continue with your next class. So quickly type in the chat if this is clear, then type Y, and then we will end our session. Yes. Yes, Gayatri, Bhavna, Omkar. So if this is clear to you, so this was the basic idea. But the more important part for us is, yes, you should understand what was happening, how it was happening. But the important things for us is the formulas that we will be getting from all of these concepts, and then we'll be applying them in the numericals. But yes, you should have an idea what was happening, what is it that they were not able to explain, why did they came up with the theory that said that your light behaves as a particle. So in tomorrow's session, we'll see how did Planck explain that your light, it is behaving as a particle, and what is the formula that he gave for the energy. So with this, I'll see you in the next session, which will be tomorrow, and we will be learning about the Planck's quantum theory. Also make sure that you solve the numericals and send your answer. I didn't get any answers for the previous assignments also, and the questions that I gave in the sessions for the some basic concepts of chemistry. So make sure that you solve the problems and then you send it to ma'am. Okay, then see you all in the next class. Yes, Chandrika ma'am.
Yes, ma'am. Thank you, ma'am.
Okay. Okay, ma'am.
Yes, students, I have shared you the next class link. So please join through that link for the next class. I have shared you the next class link in the group.